Okay, recording have started. Oh, right. So today's we will go into a new chapter, okay, or new sections, okay, on steady state error. Okay. So the goal of these sections would be to address the course outcome number 3, which is the ability to analyze the transient response and the steady state error of the control system. So we are looking at the steady state error. All right. So before I proceed onwards, okay, just a quick informations for all of you. Okay, for tomorrow test, okay, those who will attend face to face, okay, the locations would be at Magma Lukisan Kejutraan, okay, Aras 2, okay, level number 2, okay, means when you go into the elevator, you just press 2, okay, there is 1 is the ground floor, 2 is the first floor, right, at block C, okay. So this lab would be nearby the CAD lab, okay, just turn around that floor, okay. Right. So an overview, okay, so this is one of the heat exchanger process, okay, that we may see and we may want to control it, okay. So the purpose of the control system would be to maintain the temperature of the liquid at a prescribed temperature, okay, meaning to say normally fluids flow from a process, okay, they just flow, okay, through another, just flow through a pipes, okay, and throughout this pipe we would like to heat up the fluid by having an heat exchangers, okay, which would be which will use steam to heat up the fluid, okay. So fluid will go through and being heat up by this heat exchanger, okay, before it turns up to a higher temperature, I mean, okay. So over here, higher temperature. So sorry, phone call, but never mind. Okay, so for this particular temperature, okay, what we would like to have is to maintain this temperature to what we have set, okay. For example, maybe we would like to set it to maybe 100 degrees C or maybe 80 degrees C, okay. So we would have a sensors to detect the temperature, okay, and we would increase or decrease the temperature by controlling the amount of steam flowing through the heat exchanger, okay. So we have this WAF, okay, to adjust the amount of steam flowing through it, okay, before the steam convert to water and condensate and return back, okay, for to boiler or whatever to be heated up to steam again, right. Okay, so this is a typical process, okay, in factories to increase the temperature of the fluid, right. So what we can express here in the form of block diagrams or control systems, okay, would be the input, which is our original temperature, okay, the temperature before probably, okay, and then what we would like to have would be the temperature after, okay. So before and after, okay. So this is what we would like to control, right. So this input temperature, okay, can be in the form of maybe yeah, the steam temperature or the input temperature, okay, depends on how you going to model this, okay. But what we can have to control would be the WAF, okay. So we have a WAF over here, okay, to control the amount of steam going to it, okay. And then we have the heat exchanger, how good the heat is being transferred to the fluid in the pipes, okay. And then we have the sensors to actually regulate or to detect what would happen, okay. So the questions in this so-called process, okay, typical questions would be, will the system stable, the first questions, right? Or And the second questions, okay, that would come into mind, okay, that where we try to address, okay, would be, will there any errors? Okay, so errors will occur. Okay, what we refers to the error is over here would be, originally we have set a temperature. Okay, we would set it like 80 degrees Celsius. Okay, we want the fluid coming out from the heat exchanger would be 80 degrees Celsius. Okay, but then what actually comes out probably 85 or 83 or maybe 78 degrees Celsius. So there is a difference between them. So there is an error between them. Okay, so we call that as a error. All right, and here when we say steady state error, referring to even after you do not change anything, okay, the system have been stable, the error still occurs. So it will never reach maybe 80 degree that we set originally, right? So that is where we want to identify what is uh, the error that would occurs over here. Okay, so we may set over these examples, we put 90 degree, okay, we set it, desired temperature would be 90 degree, okay, then probably it will respond in second order systems form, all right? Okay, it will overshoot before it returns, okay, or maybe in a first order form, okay, after you solve all these things, okay, so it will goes up, okay, but then there is still an error over there, okay, the difference between the desired 90 degree as well as the steady state final value, okay, of your system. Okay, so the definitions of the steady state errors would be the difference between the input and the output for prescribed test input. Okay, when the time is infinity, means the time is long enough for the system to be stable, right? So typically we would use a step, okay, which is the normal constant, okay, just like these examples, okay. So when we set 90 degree, okay, so this 90 degree values will not change throughout the time, okay. So that is a kind of a step input that we have set into our process, okay. So another form would be in a RAM, okay, it will continuously ramp up, okay. So this probably we can say as a velocity, meaning to say we want probably the system to continuously increase in terms of maybe heat supplies or whatever it is, okay. So it depends on what kind of input that you have defined originally in the block diagrams or transfer functions, okay. Then also we may also include the kind of parabola type of input, okay, that we call it as constant accelerations, okay, in a physical form, okay. So we have positions, velocity, and accelerations, okay, and they are somehow related in the Laplace transform form, okay, 1 over s, 1 over s squared, and 1 over s cubed, okay. And for the time response, when we take the inverse Laplace, that would refers to the 1 over 2 t squared, so on, right? So that would be our steady state error, okay, after the system have become the steady, okay. So now let's assume the position control system, okay, where we would like to control the positions, the final positions of an a motor, let's say, okay. So you may want to control the positions of a motor, okay, where you input to certain positions. Let's say I want the motors to turn 45 degree, okay. So 45 degree would be my input, okay, and the output probably 45.2 degree, right? So that is the kind of output that you may expect, okay. So here we may have the step input, okay. For example, so you set 45 degree, okay, as a constant positions, okay. Then the ramp input itself refers to the constant velocity, where now the input of the to the positions will increase linearly. Okay, in order for you to reach to that particular positions, you may have to how should I say, okay, put it in a way like if you apply a constant velocity, okay, therefore the positions will continuously increase. Okay, so we call that as a constant velocity, right? So this constant velocity refers to the velocity of the motor. Okay, so if you put maybe 1 degree per 1 microsecond, okay, therefore the motor will continuously increase the positions, okay, to 2 degree, 3 degree, and so on, so to form a kind of ramp input, okay, in this kind of input graph, right? Then for the next one would be the parabola, which refers to the constant accelerations. Okay, again, if we set a constant accelerations, probably every 1 second, the accelerations of the rotations would increase by 1 degree per 1 microseconds. Okay, so means after 1 second, it will increase to 2 degree per microsecond, and so on. Okay, so again, when we plot the graph in terms of the positions, okay, this would be the graph of the positions. Okay, it will form a parabola, so it will slowly and exponentially increase. Okay, that would be the type of position input. Okay, when we applies a constant acceleration to our system. Okay, so next would be the source of the steady state error. Okay, for sure, they can come from various sources. Okay, especially the nonlinear sources. Okay, for example, for a gear itself, there is a backlash. Okay, so meaning to say, when you turn a motor in a clockwise, okay, then after you stop, okay, and you turn it anti-clockwise, okay, the gear itself, there is a gap in between the two mating teeth, okay, where there is no direct drive, okay, between the gears. Okay, so there occurs a kind of backlash where there is no response in maybe in 0.01 degree. Okay, you rotate, okay, that particular input, okay, or yeah, the particular input will not give the any output. Okay, we call that as backlash in the gear. Okay, so yeah, there is a lot of problem that may occur, okay, in any or any system itself. Okay, but for this course, we would only concentrate on the steady state errors. Okay, we do not consider all these non-linear type of system, okay, or errors. Okay, so probably most of this steady state error, okay, would be due to the configurations of the system. You may not set it correctly, okay, or maybe the type of the input that you supply is not correct, okay, it's not proper for the system itself. Okay, therefore the analysis using block diagrams, or maybe nowadays you have Scilab or MATLAB, okay, you can simulate earlier, okay, to see how it would respond, okay, before you actually implement it, right? So since we are concerned with the difference between the input and the output, okay, after the steady state have been reached, we limit our considerations to a stable system. Okay, so for a stable system, the natural response will approach zero. Okay, which we say the time is infinite, right? So again, unstable system we would not consider. Okay, we only consider steady state. Okay, for a stable system. Okay, for a stable system. So unstable systems, which represents losses in control, we will not consider it. Okay, for the steady state checking. Okay, in the next chapter, okay, we will learn how we can identify whether the system is stable or not. Okay, and that is where you have to first check whether the system is stable, then only you look for the steady state error. Okay, if the system is unstable, then you do not have to check for the steady state error anymore, because it will never be a steady state. Okay, so the system will never settle down, right? So for an unstable system. Okay, so here their notes would be the system must be checked for stability, right? Which we will learn in the next chapter, right? So for now, we just consider that all these systems are stable and they have settled to a steady state value, right? So how we can evaluate the steady state error? Here is a figures, okay, that shows the step input and two possible output. Okay, so when we put a step input, okay, so this would be the step input from starting from 0 second, we put an input. Okay, so we hope that the output will reach to the same input that we desire. Okay, for example, in the earlier examples, okay, 90 degree for our set temperature. Okay, so we hope that the temperature of the fluid will actually reach 90 degree, okay, when it becomes steady, okay, or stable, right? But this is where we have a zero steady state error. Okay, so the output one, zero steady state error, and there is a possibility that there is a finite steady state error. Means no matter how long you takes, okay, there is a difference between them, right? So this probably due to the configuration of the system itself. Okay, for example, you may install the heat exchangers, and the heat exchanger itself have a limit of heat transfer. Okay, so no matter how much steam you adjust, okay, because you have been limited by the opening of the valve, right? So if you have opened fully of your valve, okay, the amount of steam only can supply this kind of heat. Okay, therefore no matter how much you set, it will never reach. Okay, so means you know from the simulation itself, okay, that this value that you intend to set is not reachable. Okay, so there is a finite steady state error that will occur. Okay, so that probably comes due to the configuration of your system. Okay, the next type of steady state error would be come from the RAM input. Okay, so if you are putting a kind of RAM input over here, okay, so this is your input, okay, and we desire that after some time, okay, our output will match this input, okay, to become like uh, in the RAM form. Okay, so let me draw further. Okay, so for example, this output number one. Okay, so it may maybe oscillate a little bit, okay, but then after sometimes it will just go all along the way of this input. Okay, so in that case, in the steady state, we say zero steady state error. Okay, then for the second type of output, you may see that there is always a finite value, okay, between them. Okay, again, this is very similar to the first case lah, right? So parallel all the way, okay, you will just have the same values, okay, difference between them. We call that as the finite steady state error. All right, finite means there is a numbers of it lah, right? Okay, then for the third one would be the case where the steady state, as you can see, it will continue to grow in this way. So no matter how it is, okay, so originally probably the error is maybe, let's say this is 2, okay, then on the next second, okay, it become 2.5, okay, so as the time increase, the error become larger and larger. Okay, so this is where we would say the steady state error is now infinite. Okay, so we have three type of output. The first one would be zero steady state, zero steady state error. The second one would be the finite steady state error, and the third one would be the infinite steady state error. Okay, so you would expect or you can predict these three type of uh, steady state error depending on the system. Okay, so what we would like to see, okay, from this kind of knowledge is that is there relationship between the type of system and the type of steady state error. Okay, so here we will start to explore this idea whether there is really a relationship between them or not. Okay, so that if we know the type of system, okay, have a relationship with the steady state error, then we would know what kind of input to be given to the system, okay, to avoid all this unnecessary steady state error. So let's take this closed loop control, right? So there can be in the form of like forward, okay, forward type, okay, so forward type of feedback, okay, so we put that as the transfer function would be TS, okay, input, then we do the comparisons right after the output of the transfer functions, okay. Then there is another type of feedback type, okay, the typical one that we may use all the time, okay, which we do the output, then from the output we compare it with the input, okay. This one is input directly compare with the output, okay. In the way of the diagram itself, it may look slightly different, okay, but then what we can see is that when we do this kind of block diagram, what we see is the output would be the arrow, okay, that would be the arrow itself, okay. So this would be the arrow itself, and then for the feedback type, okay, the feedback type would be, you can see that input goes in, we compare the error is within the loop itself, okay. So what we see as the output is the output, okay. So that is how we can actually extract, okay, to find out what we would like to check, okay. If you only want to check the error, then you can perform in this way, okay, or arrange your block diagram in this way, okay. If you would like to see the output, then you can form it in this way, right? So this is how we can rearrange our block diagram, but still it is a closed loop control system, okay, where our main purpose is to see the steady state or the final value of our error, okay, whether the error will increase or decrease and so on, right? So in the system, okay, let's take this feedback loop system, okay. We may take, as usual, we use R as the input, the C as the output, and the E would be the R minus C, okay. The R minus C, we will get the error, right? So in the steady state, okay, if the C is equals to R, okay, when the C is equals to R, then the error difference would become zero, okay. In this case, we have a zero steady state error, okay. But if there is a finite value or non-zero value, okay, therefore the error cannot become zero, okay. And this would be mainly due to this value. We call this transfer functions value as a gain k, right? k is a constant. Probably it can be 1, 2, 3, okay, any numbers, okay, that adjust or change the or magnify the input to the output itself, okay, we call it as a gain. So probably it reduce to the gain itself, okay. So therefore, by virtue of the configuration itself, the error must exist, okay. It can be exist due to the value of this transfer functions, okay, this value k, okay, the gain itself, okay. Because if the gain is 1, okay, so when you go out, okay, we put input is 1, gain is 1, output would be 1, 1 compare it with 1, then we get 0, okay, very straightforward, okay. But then if the gain is, let's say, 0.8, then 1 put multiply by the transfer function, we get 0.8. 0.8, we compare it back, then the difference is 0.2. So 0.2 multiplied by 0.8, then we get 0.12 and so on. So it continues to loop, right? So the error is mainly due to the setting of this gain value, right? So now, since we know that this gain or these transfer functions will play a role in determine the steady state error, okay? So if this steady state error, this C steady state, okay, and the output, okay, the output of the steady state, C steady state, okay, and the steady state error, E steady state, okay, are given as such, okay. We just put E steady state and C steady state, assuming it's already reached the steady state cases, okay. Therefore, the C steady state should be equals to KE, right? Because we always use E multiplied by K to get the output, right? So the output should be equals to K multiplied by E, okay? When the system have reached to a steady state, so that when we start to compare it back, then it will become 0 again, right? So the error will turns to 0, minimize the error will turns to a smaller and smaller value until one time, then this system will not need to adjust the value, okay, because it's already reached a steady state value, okay. So therefore, what we can rearrange from this would be the error of the steady state would be equals to 1 over k of the output, okay. Just bring this over here, so we have this relationship, okay, between the error output and the transfer functions of your system, okay, the k itself, right? So here, this k, as we know, if since this is at the denominator's region, the larger this k value, then the steady state error would be smaller, okay. The larger it is, the smaller your steady state error, right? So if you have 1 over 1, then your steady state error will be the C steady state, okay. But if you have 1 over 1 million, then your steady state error would be much smaller, okay, which is 0.00001, okay. So that is how they are somehow related, okay. So in order to reduce the steady state error, we intend to increase the gain of the system, okay. So this is how we can relate, and then we use this knowledge to actually tune our system, okay, such that we can remove the so-called errors in our system, okay. So if the forward path gain is replaced by an integrator, now we replace this with an integrator instead of the gain, okay, the gain type of transfer functions. Okay, now we put it as an integrator. Why we call this as an integrator? Because in Laplace transform, functions divided by s, actually we are doing the integrations, right, based on the Laplace form. Okay, so therefore if you have a transfer functions, okay, a constant divided by s, okay, that over s we call it as an integrator. Okay, so now let's say our system have an integrator now, okay, which as you will get familiar later on, as there is integrator, differentiators, okay, and then the gain, okay, the gain we would call it as a proportional, okay, later on, which form the words called p, I, and d. Okay, so there is a control due to the gain, control due to the integrator, and also a control due to the differentiator, right? Okay, that would be further explained, okay, in the later stage, right? But now what we intend to do is we would like to see the effect of all these component. Okay, the first one would be the gain, which is the proportional transfer functions. Now is the integrator. Okay, so what happens if we put an integrator in the transfer functions here? It would cause now the output increase when the error decrease. Okay, when the error continue to decrease, now the output will increase. Okay, so it's like inversely proportional now, right? Okay, so the decrease will continue until the zero errors is achieved. Okay, but there will still be a value for CT. Okay, since the integrator can have a constant without any input. Okay, you may not have a you may not provide any input over here, but the system will continue to run due to the k over s over here. Okay, so that is the the response type, okay, or the steady state error, okay, due to the integrator. Okay, next would be we further look into a detailed form, okay, of how we can probably estimate, okay, from mathematics, okay, for all this statistic error. Okay, we do not want like we know it increase or decrease. Okay, we would like to know what is the exact values now. Okay, can we estimate it? Okay, so this is where we would see, okay, if we put our control system in this form, okay, this closed loop form system, okay, input, okay, and integrate to the output. Okay, so what we can see here is to find this error, okay, the error between the input again is given by this formula. Okay, error equals to input minus the output, right? Okay, and we also know that the output can be obtained by multiplying the transfer functions with the input, okay, RT. Okay, therefore now when we substitute this over here, then the error will be equals to R multiplied by 1 minus T, okay, which is the transfer functions. Okay, so now based on this knowledge, okay, we would use mathematical methods, we call it as final value theorem, okay, to find the steady state error. Okay, so we already have this so-called error functions, and we would like to see, okay, when the time is infinity, okay, when the time is large enough, okay, what would be the error? Okay, so this is where the mathematical knowledge is being applied now, right? The final value theorem. Okay, so here the formula would be the error, okay, when the time is infinite or large enough. Okay, therefore it can be equals or estimated by taking the limit when the time is infinite, okay, for our functions, our arrow functions, okay. And when we take this in the Laplace transform form, all right, so we have take the limit when the s time infinity, the s is equals to 0, okay, approaching 0, okay. And this et would become ses, okay. So this is the limits, okay, or the final value theorem, okay, for a Laplace transform, okay. So when we take this, okay, so we just have to remember this formula, okay, e infinity equals to limit s approaching 0 set, okay. Since most of our transfer function is in the Laplace transform form, right, so you would solve it using this, okay, unless the system give you in the form of a time domain, then you can use this, right. So now how we apply this further, okay, so you know that the error functions would be the r multiplied by 1 minus ts, okay. So from there we can actually estimate or calculate, okay. So take this as an example so that you can visualize how it may looks, okay. So take the transfer functions, okay, would be 5 over s squared plus 7s plus 10, okay. And we use the typical unit step as the input, okay. So what we need to see here is that we have these transfer functions and we can estimate the error, okay. The error itself is given by this, okay. You just use this formula, okay, to form this, right. You just have r 1 over s and your error 1 minus t, okay. You would get this value, okay. Once you get this value, now substitute over here, okay, into your final value theorem, okay. So what you would see now, okay, this you have to multiply by an s over here, so eventually this uh, arrow transfer functions or arrow signal itself, okay, multiplied by s, so you have an s over there, okay. So what we can see here is that when s approaching 0, so here the s can be cancelled out, right, when s cancel out. So when s approaching 0, so what we would do is h s approaching, first we cancel out these two since it can be cancel out each other, right? So now this s approaching 0, so s squared will become 0, this one will become 0, 7s s approaching 0, so this whole term becomes 0, this whole term becomes 0. So eventually we get 5 over 10, which is 1 over 2. So meaning to say, for these transfer functions over here, when we apply a unit step to these transfer functions, eventually you will get a steady state error of 1 over 2, which is 0.5. Okay, so this is how you can estimate the final value or the steady state error. Okay. Then the second one would be in a feedback control form. Okay, instead of putting the E, okay, at the right hand side, okay, now we put the output at the right hand side, okay. So again, normally we may take the h, okay, which is the feedback transfer functions over here would be 1, okay, a unity feedback, okay, we call it as a unity feedback. And similarly the implications would be very similar. Okay, we use to express the error first, and then from the final value theorem, we would evaluate or estimate the steady state error. Okay, so how we can do it? Okay, same procedure. Okay, same relationship. Okay, error is the input, the feedback, uh, the input minus the feedback lah. Okay, the output itself. Okay, then also the output can be obtained from multiplications of the error. Okay, the error itself. Okay, instead of input, now there is error over here. Okay, multiply by the transfer functions. Okay, substitute them into it, then we have this form, okay, of transfer functions to describe the error. Okay, then applying the steady state, the final value theorem into the steady state to obtain the steady state error. Therefore, we would have the SR divided by 1 plus GS. Okay, so this form would be applicable when the transfer functions diagram looks in this form. Okay. Previously, this form of final value theorem is applicable when the transfer block diagram, okay, looks in this form. Okay, so there is a slightly difference in terms of derivations, but as you can see, the derivation is very straightforward. Okay, you just have to derive accordingly and get the final value theorem, right? So once we have the final value theorem over there, then now again we will start to evaluate. Okay, what would be the type of steady state error, okay, occurs when we put different type of input. Okay, we start with the step input. Okay, when the the input is 1 over s, sorry. Okay, so input is 1 over s, so you just substitute into the previous equations, so eventually you will see that this will cancel out. Okay, so it become 1 divided by 1, since this one limit is applicable, distributable to the others terms itself, so you have 1 divided by 1 plus limit s approaching 0 for gs. Okay, so here the main part would be this. Okay, so the terms limit gs is the gain of the forward transfer functions. This one is the one we have previously, right? Okay, and due to that, we only look at this. Okay, so now when we look at this particular forward transfer functions, the gain of it itself. Okay, now in order for us to have a zero steady state error, okay, in order for us to get this become 0, okay, we would like to have this value as high as possible. Okay, if you have 1 over 1 billion, okay, then the value will be very much close to the 0, right? Okay, so this is the idea of why for this particular system or block diagrams, we would want this limit gs to be as high as possible. Okay, if possible, infinite, right? So that we get a 0 over there. Okay, so to satisfy these particular conditions to achieve our desirable steady state error, the denominator must be equals to 0, and therefore we would take this partial fractions, yeah, partial fractions, or we break them, okay, because we know that the possibility of the transfer functions can be in this form, right? The s plus 0, first 0, second 0, and so on, divide by the Sn. It can be in the form of S2, okay, then S plus 5, okay, your pool, okay, let's say you have this s plus 3. Okay, so this is the general form of this kind of transfer functions. All right, so what we noticed that from this general equation itself, in order for us to have infinity limits, okay, over here, okay, we would want this n to be at least 1, okay, at least 1 pole, okay. So this is an important characteristic, okay, for this type of system, okay. When the step input is applied, okay, the n, which is this one, must be at least 1, okay. So meaning to say, if your system transfer function is in this way, okay, s plus 3 divided by s plus 5, the n is now become 0, right? Because s0 is 1, okay. So if this is 0, meaning to say this transfer functions, okay, when we apply a step input, there is a steady state error occurs, okay. In order to eliminate, therefore we must have at least 1, okay, or 2 or more, okay. So that is the idea behind it. Right. Then we would call that as like S in the frequency form, okay. We call that as a integrator, right? As we say, 1 over S, okay. So at least 1, okay. So we say that the integrator form must be present, okay, for this kind of system when the step input is inserted, okay, to the system, okay. If there is no integrations, there is no integral components in the transfer functions, okay, then the n equals to 0, and there will be a finite error, okay, which will occur. Okay. Right. So meaning to say, for this particular form, okay, there will be no non-zero finite error, okay. So this is how the characteristics of the integrator in the transfer functions, when we apply a step input, will result to the different type of steady state error. Okay. It may now looks a bit confusing, but in real, you just have to calculate to get the value. Then you immediately you would know the answer. All right. But after some times, okay, when you keep practicing, then you will notice that these characteristics occurs, and immediately, without even solving, okay, just by identifying the type of input, okay, and the integrator itself, okay, whether there is integrator or not, then you would know whether the errors would be 0 or there is values, okay, that you may need to calculate. Okay, so next would be when we test it with a RAM input. Okay, so when the RAM input would be 1 over S. Okay, so for 1 over S system, okay, so immediately the system will now become in this form. Okay, we only look at this particular part, okay, since this 2 is S plus SG, so we can combine them together, right? So in this form, okay, this would be cancelled out. Okay, so you will get this particular form, right? So once we get this form, okay, so again we would compare with the general form of transfer functions, okay, and in order for us to get a 0 steady state error when a RAM input is inserted, okay, the n value must be now at least 2, okay, at least 2 instead of 1 previously. All right. So if only one integrator exists, okay, in the forward path itself, then there will be a finite uh, values. Okay, there will be a finite steady state error. Okay, if it is 2, then there is 0 steady state error. Okay, but if less than 1 now, okay, if it is less than 1, then you will start to see that the continuously increasing steady state error will occur. So the kind of infinite steady state or non-zero type of steady state will occur in that form, right? So if there is no integrators, the steady state error would be infinity, okay, for the RAM input. All right, so you can see that it's continuously to grow, okay, and there is a relation, okay, shape that you may later on observe, right? Then again, when as we continue to increase our form of test input to from step to RAM to parabola and parabolic, okay, then this n will continue to grow, right? From 1 to 2 to 3 now, okay? At least 3 to have a 0 steady state error, right? If it is not, therefore, less than 3, okay, means 2, then you have a finite steady state error. In then 1 or 0, you may have an infinite steady state error. Okay, so 1 or less, then you have an infinite steady state error. So you can see that the requirement is higher and higher, okay, as we increase the the, the order of our input, okay, from the step, okay, the order is just 1 over s, okay, then increase to RAM 1 over s square, okay, now the order increase to 3, then the n must be at least 3, okay. So it changed according to the type of input. Okay, that's why when we know all this knowledge, then we will know that the input and the system will have a relationship. Okay, to so that they are matched and to produce the kind of steady state error that we would want. All right. So again, we go through simple examples over here. Okay. Find the steady state error for the input of 5 UT or 5 unit, okay, then the 5 TUT and 5 TS, a T square UT, all right, meaning to say this would be a step input, RAM input, a parabolic type of input, okay, because UT is a step input, right? So 5 times the step input, so it's just a step input, okay? Then TUT, then the order will start to increase and so on, right? So we just take this as examples, and this is a feedback loop of a system, so we would consider this as a GS, right? Okay, so meaning to say we would just apply or look at all these limits, okay, depending on the type of the input itself. Okay, so we just look at the limits itself. Okay, final value theorem. Okay, so here, as we say, this is first we should know what type of input we have. Okay, so since this is a step input, therefore we only use the final value theorem for the step input, which is given by this. Okay, given by this. So again, you have to distinguish, right? So this one, this, and this, okay, it's only for you to quickly check, okay, quickly check whether there is a steady state error, a finite steady state error or not, okay? If you would like to calculate the steady state error, the value itself, this would be your your equations. Okay, you still have to depends on the final value theorem itself. Okay, so you still have to depends on these equations. Okay, so here we just apply the correct equations over there. So here is 5 divided by 1 plus limit gs, right? Then once you put it everything, then you found that it is 5 over infinity, you get 0. Okay, so this refer to a zero steady state error, right? So this is how you can calculate. But if you do not want to calculate, or the questions only want you to predict, okay, if it is predict, then probably you may not need to even calculate. You just have to observe the characteristic of the transfer function. So this transfer function itself, the n value would be equals to 1, right? So meaning to say, when this equals to 1 for a step input, the steady state error would be 0. Okay, but then system, the n is 1 when the input now increase to a ramp. So this is a ramp input. Therefore, now the problem will start to occur. There will be a finite value, okay, which is 1 over 20, right? Then we further increase to a parabola, okay, parabola type of input. Therefore, we will get an infinite, okay, as we can see that from 0, same system from 0, okay, when the step input is applied, we change the form of the input to ramp, then there is a finite steady state error. And when we change the input to a parabolic type, then we get an infinite errors, okay, infinite steady state errors. Okay, so the equations is very similar, right? The only difference here is just you apply the same equations, okay, as shown, okay, and the input, there is a 5, 5, and 5t over there, right? So you just have to input that into your equations, right? For this one, instead of 5, it becomes 10 because 5t square ut, okay, when we take the Laplace transform, is 5 dot 2 factorial. So 5 times 2, you get 10, right? So when we increase, then this input contributions would be further increased. That's all. Okay, so that is how you can estimate the final value or the steady state value from a final value theorem. All right. Okay. So next would be just an exposure to what we call a static error constant. Since we always consider certain parameters, okay, so we would now try to set such that the system or many control devices, okay, the devices itself, okay, they may ask you for all this input, okay, they call it as a static error constant. Okay, so what we can see, there is this kind of relationship, okay, for a step input the error would be this, the ramp input the error would be this, and so on, right? Okay, so what happened is that we now try to form a constant, okay, that we would always refer to, okay, since we actually do not need to estimate the exact error, okay, we may not need to, okay, we only need to know whether the error is finite or 0 or it is acceptable or not, right? So therefore it is more convenient for most of the control engineers to communicate in a form like a static error constant, okay? So we will have the kp, kv, and ks, okay, which is the limit g, limit sg, and limit s square g, okay, which corresponding to this, okay. limit g, limit sg, limit s squared g, okay, to corresponding to different type of input. Okay, so when we use for different input, the arrow would have slightly different notations over there. Okay, and that constant is much more easier to compare, right? Easier to compare, right? So these quantities depends on the form of g, okay, and from there we can assume the value of zero, finite, constant, or infinite, okay, depending on this. Okay, so if you get this value, a very high value, meaning to say you get zero constant, zero steady state error, right? So if you get not too high, okay, then you will have a finite constant. And if you have this value very small, okay, then you will have a so-called infinite type of error. Okay, so this steady state error constant appear in the denominators, okay, to tells you how it may affect, right, the inverse proportional relationship between them, okay, between the steady state error and the error constant. Okay, so again, a quick examples over here. Okay, same type of feedback loop, okay, with a given transfer functions, okay, and this we will know that the system have zero, okay, as zero over here, okay, we only have pools and so on, right? So without solving for the statistic error, we just have to observe the static error constant for different type of input. Okay, so for that we just have to check what is the kp, kv, and ka, right? So kp just put in, okay, 500 times this and so on. Okay, when s equals to 0, when s equals to 0, okay, when s equals to 0, 0, and 0, okay, therefore there is 500 times 2 times 5 divided by 8 times 10 times 12, okay, you get 5.2208, okay. Then we get the kv equals to 0, okay, the ka equals to 0, right? So meaning to say, from this value itself, okay, since we do not get something like infinite or very high, meaning to say there is a finite error, okay. So the finite error would be 0.162 if we would like to compute it correctly, right? So it's 1 over 1 plus kp, okay, which is 0.161. Okay, for the RAM input, our previous formula would be this, right? 1 over the kv, okay, this one would be 1 over ka, right? So just put it in, then you will see that there is an infinite steady state error occurs, okay, when we change the type of input for this particular feedback system. Okay, so this is how it would looks like. Okay, so now when we start to use the n, now we start to change to 1. Okay, what would occurs is that the kp now would become infinity, okay, means the steady state error would be 0. Okay, kv would be a finite value, okay. Then another meaning would be the error would be a finite value, okay. And when the ka is 0, then the parabolic the error, steady state error for the parabolic would be infinite. Okay, so inversely related. Okay, infinite, 0, 0, infinite. Okay, so inversely related because it is at the denominator. Okay, the static constant. Okay, so same thing when we further increase the order of the system or the type of system. Okay, then you can see that this become infinite, and a finite value. Okay, so the statistic error will be 0, 0, and a finite value. Okay, so this is how you can relate, okay, the type of input and the type of system. Okay, and from there you can estimate, okay, whether errors will occur or not, okay, even before you start to solve them, right? So this is what we define as a system type. Okay, system type. Okay, for a feedback system, then you realize that from n equals to 0, n equals to 1, n equals to 2, we start to define this as a system type, right? So in the system type itself, then we will have when n equals to 0, then we define that as a type 0. Okay, therefore you would see the different relationship, okay, between the static error constant and the error itself, okay, for different type of input. Okay, so two things over here. The one is the type of input, and the second one would be your system type. Okay, the transfer function itself. Okay, so when they are matched together, okay, so when this is 1 over s, okay, that means type 1 for the input, okay, type 0. So you can see that type 1, 0, right? It start to 0, okay? Type 2 start to 0. Type 3, then the 0 would be here, okay, when the type is 3 or more, right? So this is how you can quickly check, okay, or predict before you have to do all these calculations, right? So we will stop over here, and yeah, let's check if you have any questions. Any questions from you? If no questions, we would end these sessions and see you tomorrow, right? So for tomorrow test, it would be open book, right? Open book, since you have friends at home, okay, and so on. So open book, okay. The only difference is that if you come face to face, it will be easier for you to submit, right? You don't have to scan or whatever it is, okay? No internet problems and so on, right? So if no questions, then we will call these sessions to an end, okay? And see you tomorrow, right? So for those who are taking the test online, you just have to come into the Google Classroom, right? So all the tests would be released over there, okay, in the Google Classroom. All right. Okay. See you and thank you.
Thank you, Doctor.
Oh, hi, Dr. Chua. Can you hear me? Can I ask something about assignment one? It's about the using MATLAB to obtain the time response.
Okay.
Is it okay if I just use the MATLAB to obtain the time response
Yeah.
without putting the simulating blocks?
Yeah, no problem.
Okay. Does it mean that I just put in the transfer function and then get the step response graph? That's all?
Yes.
Okay. How about the show all the relevance characteristic? Does it mean that I need to show all the time constant, rise time, and setting time?
Yes. From the time response, you can get the time and other things.
Okay, all right. Okay, that's all from me. Thank you, Dr.
Okay.
Chua.